Hi, Chris Good here, and we are still talking about the two-way analysis of variance, and in this presentation I'm going to try to give you an idea of how to interpret main effects and interactions. Remember, the main effects have to do with the overall effect of one factor. That in a two-way analysis of variance, you're actually looking at two different factors, two different independent variables. Let's go to an example so I can point out a couple of features. So in this example, this is the Martini study, where we're comparing the effects of, well, we're not comparing effects, we're trying to measure the effect of alcohol on the number of errors someone might make when giving a speech, a prepared speech. So basically you have people come into the laboratory, you give them either a martini or an identical placebo cocktail, and you have them read a prepared speech on camera to either a large audience or a small audience. So there's two factors that we're manipulating here. There's two levels of one factor, whether they get alcohol or not, right? And two levels of the other factor, whether you're addressing a large audience or a small audience. When we do our two-way ANOVA, we're going to get three values for the ANOVA statistic F. The first F will test for a main effect of the first factor. Let's call that drink type, right? Whether you're drinking a martini or a placebo. The second F will test for a main effect of the second factor, which is audience size. And essentially, these two main effects, the two Fs, the test for main effects, will help you determine whether there's a difference between first, the martini groups together, sort of averaged together, and the placebo group. The second F will tell you whether there's a difference on average when addressing a large audience or a small audience, regardless of what they drank. So first, you're looking for difference between both the martini groups, and regardless of whether they addressed a large audience and a small audience, and both placebo groups. To do that requires you to sort of, if you're just looking at the graph, you can kind of eyeball the difference between the, I don't know, the midpoint between the large audience and the small audience. So if the large audience martini group made 9 errors, right, that's the height of this bar on average, and the small audience martini group made, what is that, 5 errors, so 9 and 5 kind of averages out to around 7, right? So on average, the martini group is making like 7 averages, regardless of which audience they addressed. The placebo groups, both the large and the small audience placebo groups, are making 10 errors on average. So if the martini groups together are down here at 7, the placebo groups are up here at 10, right, regardless of audience size, then overall the main effect of drink type is that people drinking the martini make fewer errors than the placebo group. Okay, so that's regardless of audience size. Let's take a look at the main effect of audience size. So if we average across the martini and placebo group, then on average people addressing a small audience are making around, well, let's see, they're making 10 errors in the placebo group, around 5 errors in placebo, so 7.5 errors is about how many errors the small audience group makes. Up here, it's more like 9.5, right? 9.5 errors for the large audience when you average across drink type. So the overall or main effect of audience size, when you ignore what they were drinking, is that people addressing a large audience make more errors on average than people addressing a small audience. Well, you can see that that main effect of audience type, well, whether you address our large and small audience is kind of different depending on whether you're drinking a martini or a placebo. But that doesn't have anything to do with the main effect. That's the nature of the interaction. So we talked about two main effects, drink type and audience size. But the third F in your two-way analysis of variance is testing for an interaction. And an interaction occurs when the effects of one factor are different at different levels of the other factor. That's pretty confusing to hear, so let me try to say it a different way. It's when the effects of one factor depend on what level of the other factor you're at. Let's take an example here. Clearly, martinis are reducing the number of errors that you make when you're addressing a small audience. So when you take a placebo, you make 10 errors, and when you take a martini, you make 5 errors. There's a lot of reasons why this might be true. Alcohol could be relaxing these folks, but not so much where they can't speak properly. So you're a little nervous when you're giving a speech, and maybe the martini alleviates some of that anxiety. Does it work the same way when you're addressing a large audience? Well, it works in the same direction. People drinking the martini make fewer errors on average than people drinking the placebo when they're addressing a large audience. But this effect isn't as big as it is when addressing a small audience. So here, the effect of drink type is different when addressing a small audience than when addressing a large audience. And on the next quiz, you're going to have a whole bunch of questions that ask you to explain the nature of the interaction just by looking at a graph like this. One thing that'll help you is if you can draw lines like this. So in a bar graph, I've drawn a line connecting the large audience martini mean to the small audience martini mean, and another line connecting the placebo large audience mean to the placebo small audience mean. Now, you won't know whether you have a significant mean effect or interaction until you do the statistics, but the fact that these lines are going to cross out here, right? They're not parallel. The fact that these lines aren't parallel suggests that there is an interaction there. But that's not what I'm asking. What I'm asking is, what is the nature of this interaction? An interaction means that the effects of one factor, here drink type, are different at different levels of the other factor, here audience size. So when I ask what the nature of the interaction is, I'm asking how are the effects of drink type different in a small audience, in front of a small audience, than they are in front of a large audience? And the answer here is simple. The effects of alcohol here are greater in front of a small audience. So alcohol overall decreases the number of errors, but it decreases them more when you address a small audience than when you address a large audience. Now, there's lots of different ways that this could have turned out, and we'll talk about some of those in a couple of example problems, and I'll video those later on. Right now, I want you to imagine what this graph would look like if we got rid of the bars and just had these lines. It's kind of a shorthand for a two-way design like this. So I'm going to show you 8 graphs. These are the first 4, and I'll show you the next 4. And these are different ways that the results of a study that a study in which the effects of alcohol were tested again, but also the effects of expectation. So 2 factors are manipulated here, and this is kind of like the Milgram study that we've discussed before. There was an example on a recent quiz. So here we have a group of people that's either drinking alcohol or not drinking alcohol, and what we're measuring is how much they will shock somebody as a punishment for I don't know, like cheating or something like that. Now, nobody actually gets shocked. They're just turning a dial to indicate how much they would punish somebody if they actually could. And what we don't see here are the bar graphs. What we would see if there were bars, where there would be a bar in the no alcohol group for the mean of folks who weren't expecting alcohol. So these are people who we didn't give alcohol to, but we didn't tell them they were going to get any. We also have another bar here that would go up to where the endpoint of this line is. And that bar would be the mean of people who expected alcohol, but they didn't get any. So we gave them a placebo, but we told them that there was alcohol in it. And this is interesting because we're not only manipulating whether they got alcohol or not, we're also manipulating the expectations of it. And a lot of the effects of alcohol we know now are due to sort of our expectations about what's going to happen. And in class I'll give you a real-life example of that. Here on the right side of this graph, this represents two groups who both got alcohol. And there should be one bar here who got it, but they were told they weren't getting any. And there's a second bar that goes up to here where they were told that they were getting alcohol, and this group actually got it. So to describe this two-way design, we would call this a 2-by-2 design, and we're looking at the effects of alcohol and expectation on the mean intensity of a shock that people would give. Now, you can see that there's 4 different ways that these results could have turned out, and you'll recognize that there's no interaction here in any one of them. Why? Because all these lines are parallel. They don't look like they're going to cross. On the next page, well, we have this group in the lower left. It looks like these lines are parallel. They're not going to cross. So there's no interaction here. It looks like there's an interaction here, and here, and here as well. You can also, by looking at just the lines and their relationship to each other, describe main effects. I'm not going to do them all because I want you to be able to practice these when we get together in person, but for example, in this upper right hand corner, these lines, remember, are supposed to be connecting columns. So there's a column with people that didn't expect alcohol right here, and people who did expect alcohol right here. Of course, neither one of these groups got any alcohol, right? For the alcohol group, here are people who didn't expect it, right? That's the height of that bar. People who did expect alcohol, right there. So on average, right, you can look at sort of the endpoints of these two lines. This line connects the data from the people who expected to get alcohol, people who didn't actually get it, and people who did. But both of those groups were expecting to get it. This line, the do not expect line, connects the means of people who did not expect alcohol and did not get it, and people who did not expect alcohol and got alcohol. If you look in between these two endpoints, you'll see sort of the average performance of people who got alcohol, regardless of whether they expected it or not. Same deal if we move on down here. Here's the average performance of people who received no alcohol, regardless of whether they expected it or not. If you compare sort of where this is with where this is, looks like there's not much of a difference. So that would support the argument that there's no overall effect of alcohol by itself. If you look at the middle point of the line, right, this is sort of the performance, the average performance of where, of the shock that people gave when they were expecting alcohol, regardless of whether they got it or not. So this is people who expected alcohol and got it. That's where this endpoint is. This endpoint is people who expected alcohol but didn't get it. And in between, you'll find that's the average performance. Here is the average performance of people who did not expect alcohol, regardless of whether they got it or not. The middle of the line shows you where that is. If you compare the midpoints of these two lines, well, it's very clear that people who expected alcohol gave a greater intensity shock than people who didn't. Right? This is regardless of whether they actually got it or not. If you expect it, you give a bigger shock than if you didn't. So this indicates the nature of the main effect of expectation. When you expect alcohol, you give a big shock. When you don't expect alcohol, you don't. This has nothing to do with the effects of alcohol. And of course, these lines are parallel, so there's no interaction. So try it for yourself. For each one of these 4 graphs, write down the nature of each main effect and the nature of the interaction if you think you see one. All right, let me give just a couple more examples and then we'll wrap this all up. I'll show you some data that came from a study that I did. I studied the acoustic startle response as an undergraduate working in a laboratory in college when I was majoring in psychology. And we were measuring something called the acoustic startle response. So basically, if you hear a really loud noise, then you'll blink. And we're measuring the likelihood that people would blink. Out of like 100 trials, we're measuring the proportion in which they blinked. Well, one thing that we know about startle stimuli, and these are acoustic sounds that come on, they last for 50 milliseconds, and then they go off. If you heard this in the laboratory, you just hear a right? And these were actually noises that sort of came on and stayed on, but we know that sort of the onset of the sound and the offset of the sound are the most important parts. So we sort of simulated taking out the middle part by having two paired tones that went, right? Two paired sounds that represented those endpoints, right? They're just little spikes, but they represent the onset and the offset of, this sound with the same duration as the time in between these two things. So we're really taking out the middle chunk of it. So we have paired and single stimuli of varying duration, 6, 20, 50, and there was another one that was 100 milliseconds. And this is the way that the data came out. So here's another way to look at main effects and interactions. Here we have more than two groups for one of the factors. There's two groups for this factor, single or paired, but there's 4 different durations. So this is a 2 by 4 factorial design, and we're looking at the effects of whether stimuli was single or paired, that's the 2, and the effects of duration, and also whether there's an interaction between these two. Well, let's look at the main effect of stimulus type. So all these average together, it's about a little less than 50% response probability. All these average together, it's more like 65% response probability, 0.65. So overall, the main effect of stimulus type is that single stimuli, you're more likely to respond to single stimuli than paired stimuli. How about the interaction? How about the overall effect of duration? Well, then you have to sort of average the 6 millisecond together, average the 20 millisecond together, average the 50 millisecond together, and average the 100. So the averages of the 100 and the 50 look about the same, but they're bigger than the ones for the 20, which are bigger than sort of the difference between, this graph and this one, right? Or the average between those two. Average between the stripy one here and the one here. So it looks like it's increasing. So overall, the main effect of duration is that the longer the duration, the more likely you are to respond. But there's an interaction here too. How do I know which lines are not parallel? Well, if you connect the single and paired stimuli, you'll find that those lines aren't parallel to each other. That suggests that there's an interaction. And the nature of the interaction is this. How are the effects of duration different for single than paired? Well, for paired stimuli, there really don't look like there are any effects of duration. 6, 20, 50, 100, these aren't really different from each other. So this is a case where we see an effect of duration only for single stimuli and not for paired. So that's another way that the effects of one factor, duration, can be different at different levels of the other factor, which is whether they were single or paired stimuli. All right, and it turns out, in this case, all 3 of those were significant. I'm going to stop right there, and I'm going to put audio on the next slides in a separate presentation for Thursday.